Hi guys, this is lesson 1 for our course of econometrics. It is an introduction to econometrics. The main points that we will cover in this lesson are first, an introduction to econometrics, second, a discussion of the objective of econometrics, and third, a presentation of the different types of data sets that we are going to model. So first, an introduction. What is econometrics? Econometrics deals with building statistical models for economic data. To understand when a model is statistical, first let's consider an equation which is not statistical. This equation is the famous equivalence between energy and mass. Energy is mass times the speed of light squared, E equal m times c squared, very well known. In this equation, you don't have an error term. If you have the mass of a given mass and you multiply it by the speed of light, that is the potential energy that is contained in this volume of mass. This equation does not provide an error. This doesn't mean that the equation is perfect. Probably, if you liberate the amount of energy contained in a mass and you measure it, it won't be exactly as predicted, but the error is sufficiently small to be discarded. In econometrics, however, we will describe the relationship between economic variables, and all the models will include an error term. Second, modeling. What is modeling? Modeling consists in representing a data set, let's call it the sample, by means of a mathematical equation. Let's call it the model. And one builds a model because it is more useful than the raw data to meet a specific need. For example, consider a map. A map is a simplified representation of a given territory, and the map is more useful than a full-scale photo of the territory if you want to find your way and to go from point A to point B. So you rely not on a precise representation of the territory, but on a simplified representation, the model. And this happens because it is critical for the model to be useful that it is much simpler than the data it represents, but captures all the data features required for each application in particular. For example, a map for going in a car from Madrid to Barcelona, an adequate map for that will be very simple. However, a map for doing a hike in the countryside in a territory of 4 square kilometers we need lots of little details, so you can find your paths, you can find the river, you can find the waypoints to get to a given town. Last, econometric datasets have some particular features in comparison with datasets coming from nature or from engineering. First of all, economic data often has observation or sampling errors. Consider important magnitudes such as GDP or inflation. Inflation is measured as the annual growth rate on the basis of a particular price index. This price index is obtained by sampling, so it is an estimation of the volume of prices for a given set of products. This estimation is built on a sample not obtained from all the data points that you could have potentially. So when you are computing the price index, you are including in it an observation error, and when you compute inflation on the basis of this price index, you are also inheriting this error. Second, the economic data is not the outcome of an experiment, so things only happen one time. Consider again inflation. Inflation in March 2020. Inflation in March 2020 is a figure that we will estimate only once. We cannot resample time and time again and obtain different figures. We cannot estimate inflation according to our standards in Spain in this month and then move to an alternative dimension to observe this inflation again. So, in economics, you either observe a data once or you don't observe it again. And the third particular feature of economic data is that the variables are often measured in money. And money is a unit of measure very uncomfortable. And it is very uncomfortable because it changes of value over time. It is not the same to have 100 euros now than to have 100 euros 10 years ago. The amount of goods that you may buy with 100 euros now is probably much smaller than 10 years ago. The objective of econometrics. What econometrics does is applying the tools and methods of statistics to build models for economic activities with different objectives. One of these objectives could be estimating some model parameters which are not known but are relevant to our activity. For example, if we have a portfolio of investments and we are worried that a market index may fall, we could fit an econometric models relating the value of our portfolio to the movements in the benchmark index. So you can simulate how your portfolio will perform given certain fluctuations in the market. If you are comfortable with this sensitivity, okay, you are good to go. If you are uncomfortable, you think that your portfolio reacts too much to the index, you may take measures to reduce the exposure of the portfolio value to the market. Another frequent objective of econometrics is estimating unknown values of the sample. First of all, the most clear one, forecasting. You may want to forecast a given value, which is unknown, or the reaction of an individual. For example, credit scoring systems estimate the probability that a loan will result in a future default, depending on the financial and circumstances of the applicant. A second different type of estimation of unknown sample values is called nowcasting. Forecasting is estimate a value which is in the future. Nowcasting is estimate a value which happened now. For example, bureaus of statistics produce estimates of GDP for current quarter. However, the annual figure, GDP in this year, will take several years to compute. How can we accommodate the fact that GDP in, let's say, 2020 will take several years to compute, but we are now producing figures for GDP in February? Okay, what happens is that the quarterly value of GDP is an estimate obtained by econometric methods for a value which is happening now but is not known. So you are nowcasting, forecasting the current value of quarterly GDP. Another alternative is to backcast. Backcast means computing values, sample values which are unknown but are in the past. For example, historian derives estimates for GDP of inflation in past centuries using fragmentary data from different sources. So you can forecast the future, you can forecast the present, and you can forecast the past. These three problems are meaningful in econometrics. Another of the goals that you may want to tackle is to extract signals buried in the data. For example, you have a time series for an important variable, let's say inflation. You may want to estimate the trend of inflation, to make assumptions or make affirmations like inflation is moving upwards at an increased rate or is declining or is doing whatever it takes. You also may want to estimate seasonality because inflation in some months, for example, in January, may fall due to particular seasonal circumstances. For example, the price offers that take place typically in January. Another important application of econometrics consists in simulating the behavior of a system. For example, there is an important sensitivity analysis that the authorities perform on the balance sheet of a bank, which is called stress testing. In stress testing, you simulate the behavior of the balance sheet under different stress scenarios, like a large inflation, a huge unemployment figure, or whatever. And this sensitivity analysis allows the authority to assess the capital requirements for the bank. And last, if you have the ability to forecast the behavior of a system, and you have the ability to simulate the system, you may want to use your model to control the behavior of a system. So central banks, for example, estimate intervention rates that will drive expected inflation to target. So you decide the value of a control variable that will allow you to reach your goals. What types of data sets are we going to model in econometrics? In my opinion, the most useful classification is the one that splits them according to their time dimension and the space dimension. A data set can be referred to a single unit of time, or time can be irrelevant for that specific data set. And also, the data set can be composed of variables which evolve over time. This is what we call the time dimension. And the space dimension is any other dimension other than time. For example, the sample may include different units, which are countries, they are firms, they are families, they are individuals, they are whatever. This is called, in the econometric jargon, the space dimension. Or the sample can be referred to a single spatial unit. So, if all the values are referred to a single time unit, and the sample is referred to a single spatial unit, this is not a sample, this is a single data point, so you cannot do anything with econometrics. If we move upwards, this will be the starting point of our syllabus, cross-section data. Cross-section data refers to a case in which all the values are referred to a single time unit, or time is irrelevant. And also, the sample includes different units. An example would be health expenditure versus GDP for different countries. Another alternative is that of time series. In time series, the sample is referred to a single spatial unit, but the sample evolves over time. For example, we could consider health expenditure again versus GDP for a single country, that is a unique spatial unit, in several years. This will be a time series. And the combination of cross-section and time series arises in the form of panel data. In panel data, you have a time dimension because the sample variables evolve over time, and you have also a space dimension. For example, you could consider health expenditure versus GDP for several countries in different years. You would have both types of dimension in the sample. Another classifications for dataset would look at the nature of the variables. For example, the sample variables can be continuous, that is, they are real number with decimal positions, or there could be discrete, that is, for example, natural numbers. Discrete variables can be dichotomous. These are also known as binary, 0, 1, or dummy. For example, an individual may be smoker or non-smoker, but cannot be something in between. Or the variable can be polychotomous, with values 0, 1, 2, 3, 4, for example, the number of bedrooms in a given house. Let's look at some examples with cross-section data. The first example is birth weight versus number of days of gestation. Gestation is here in the x-axis, and this is birth weight. You see that you have a clear cluster of data points. Each data point is a combination of period of gestation and birth weight. Probably the children were born in different days, but we are considering that time, the time dimension in this sample, is irrelevant. We are looking at the results of the same biological procedure. It is also very interesting to see that you have here some very anomalous data points. This kid here is supposed to have been in the womb for 5 months and have a birth weight of 3 point something kilos. So this is something like Childzilla, an enormous kid. In 5 months, 3.5 kilos. When he gets older, he will probably destroy Tokyo. Or alternatively, this is a bad data point. This is a recording error, as probably it is this, and probably it is this is also a recording error. This recording errors, this bad data, may distort the relationship between the variables. Probably if we see this cluster, we will consider something like a curve going from here to there. But a regression method would fit a straight line to represent this sample. So these anomalous data points, these outliers, are something that distorts a lot in econometric analysis. I have here a binary variable. It is either 0 or 1. 0 means that the mother in the same sample that we have above, didn't smoke during the pregnancy, and 1 means that the mother did smoke during pregnancy. And you have here the birth weight of the corresponding children. As you see, the birth weight for the children of non-smoking moms has a distribution which reaches a highest data point, a highest maximum, and has a highest average. And the children from mothers who smoke during pregnancy tend to have a smaller weight. As weight is related with the expectation of survival, this is the empirical reason why medical doctors advise the moms to not smoke during pregnancy. In this case, we are considering a polycotomous variable, the number of bedrooms in a given home, 2, 3, 4, 5, up to 7, and the price. And the price will be a real number variable. So what you have here is the distribution of prices observed for homes of this size measured in number of bedrooms. You have more or less a reasonable distribution up to 4 bedrooms, and then 2 single data points that act here as outliers in the sample. Probably you are better off if you delete these data points before analyzing your sample. So in this case, you have a polycotomous discrete variable versus a real value variable. And here you have a case in which you are comparing a 0-1 variable, which is being of colonial style or not. This is an architectural style, very important in the United States. And here you have the number of bedrooms of the corresponding home. So you have the distribution of number of bedrooms for non-colonial homes and the distribution of the number of bedrooms for colonial homes. Colonial homes tend to have more bedrooms than the homes which are not colonial. Also for economic time series. This is a very famous time series that we are going to work time and time again during this course. It's the number of airline passengers all over the world. This is a monthly time series. So here you have the date, and here you have the number of airline passengers in thousands of passengers. This is an early time series that starts in 1949, I think, and stops in 1960. You have here a trending time series, meaning that the level of the variable tends to move upward. This time series also has a seasonal fluctuation, that is a pattern that repeats time and time again over the year. In some months, you tend to travel more by air than in other months. And you see also a third feature, which is very characteristic of time series, economic time series, which is the variability of the time series increases as the level goes up. Note that I have said variability. I have said variability because this time series doesn't have a stable mean, and as it doesn't have a stable mean, I cannot properly speak of variance, because to define the variance, I need a stable mean. So I spoke about variability. To be rigorous, I could also say volatility. And here I have a daily time series of IBEX 35 return in contiguous market days. What you have here is a time series which is stable in the mean, but displays a behavior which is called volatility clustering. This data happens to have small variances in some parts of the sample and large variances in other parts of the sample. So the mean for this time series is stable, the variance is not stable. The market passes for periods of low volatility where the market is quite quiet, and then periods of high volatility when the value of the market moves up and down sharply. That is all that I wanted to tell you today. Good night and good luck.